Hi everyone. So today we're going to move on to the second portion of the course, which is concerned with an object called the Fourier series, and it arises naturally in the study of functions that oscillate. So to give you an idea of why we're doing this and why we're doing it right now, I want to give you a picture of what we've done so far and then how it motivates the next step that we're going to take. This is not the order that things happened in historically, but it makes sense as a story that we tell ourselves about the sophistication of the math that we're using. So what is the story so far? Well, we've talked about series solutions to differential equations. And so the first thing that we did was we wrote down a differential equation with non-constant coefficients. So we started with the equation y prime prime plus p of x y prime plus q of x y is equal to 0, where p and q are functions. And then we assumed that p and q were analytic. So 1a, p and q are analytic, which means that they have power series. And once we've assumed that p and q have power series, then we're allowed to assume that the answer to the differential equation is also a power series. So 1b, we assume that the solutions have the form y is equal to the sum from n equals 0 to infinity of a n x to the n. So a power series solution. Then, once we had power series solutions, we took that idea and we used it to solve a differential equation called Legendre's equation. And Legendre's equation looks like 1 minus x squared y double prime minus 2x y prime plus alpha times alpha plus 1 y is equal to 0. This is an equation that can be solved at 0 using series methods, and when you do that, the last thing that we got was the Legendre polynomials and an expansion theorem. So, what do I mean? So this is one continued. So the upshot is the Pn are an orthogonal basis for a vector space of functions and f can be written uniquely as a sum of Legendre polynomials, subject to some conditions like f and f prime both existing and being continuous. So why do we do that? The big reason is that a Legendre expansion is outstanding numerically. The downside is that Legendre polynomials are not good at approximating functions that wiggle around too much. So Legendre expansions aren't good at modeling periodic functions or oscillating functions. Okay, so that was sort of the first thing that we did. So to reiterate, we started with a type of differential equation. We figured out a way to solve that whole family of differential equations, in this case the series solution. We solved a specific differential equation with the method, which was Legendre's equation. We got a family of functions that was an orthogonal basis for a vector space of functions, showed that we had an expansion theorem for any function in that vector space, and then we have an argument for why we want to do that, which is that expansion in terms of Legendre polynomials makes excellent numerical approximations. Then we did it again. We wrote down an equation of the form x squared y prime prime plus x p of x y prime plus q of xy is equal to 0. We showed that x is equal to 0 is a regular singular point. Which, for an equation in this form, just means that p and q are analytic. Now we came up with a method of solution. We assumed that we don't have a power series, but we have a Frobenius series solution instead. So we assume that y is equal to x to the r times the sum from n equals 0 to infinity of an x to the n. Of course, the existence of solutions and second solutions depends on the values of r. So off to the side, we did some work on the indicial equation. And then r, which are the roots of that equation, determine what the form of the solutions is. In practice, what that means is that we know what the solutions of the differential equation are going to look like. So with this, which was called Frobenius theory, so this was a Frobenius series, we attacked a specific differential equation. And the specific differential equation that we went after in this context is called Bessel's equation. So Bessel's equation looks like x squared y double prime plus xy prime plus x squared minus p squared y is equal to 0. When we solved this equation using Frobenius series, just like before, we ended up with a family of functions. So we got functions that are called j p of x, which are the Bessel functions of the first kind. And their relatives yp of x, which are Bessel functions of the second kind. And the Bessel functions of the first kind are the ones that we really care about usually. Those actually have behavior that the Legendre polynomials don't have. So the graph of a Bessel function of the first kind looks like this. It oscillates and then decreases in amplitude as time goes on. And if you write down a lot of Bessel functions, you end up with a lot of different functions of a lot of different orders. But they all kind of have the same sort of feel. They oscillate and they diminish in amplitude as time goes on. And that means that the Bessel functions turn out to be useful for modeling or approximating oscillating functions. So we got an expansion theorem, which says that f can be written uniquely in the form that looks like this, where the jp lambda n x just means that you find all the zeros of the Bessel function and you can construct this orthogonal family. So really what's going on in the background here is that this is also an orthogonal family, or an orthogonal basis for a vector space of functions. And you might think, well, why would I want to do that when I can already do it in terms of Legendre polynomials or Taylor polynomials? And the answer is this particular expansion theorem, because all of the pieces are oscillating functions of different frequencies, this expansion theorem is actually very, very good at approximating oscillating or periodic functions. Why use this expansion theorem? And the answer is the family jp lambda ix is an outstanding family for approximating oscillating functions. So why not always do this? After all, we have a family of oscillating functions. We can expand it, and if we have some f, we can always expand it in terms of these. It's very easy to compute what the coefficients are because we can use the inner product formulas. So why not just stick with this? Well, the knock on Bessel functions is that, one, they're hard to compute with because they're not polynomials and they don't have closed forms. They're infinite series, right? So they're hard to compute with. And two, it's not always clear how to interpret an expansion. So what I mean by that is, if I told you that I had a function f that was equal to, say, I don't know, 2 times j1 of lambda 1x plus 3 times j1 of lambda 3x. I mean, that's a totally valid function. I can certainly compute the first 0 of j1 and the third 0 of j1 and plug them in and make functions and build this out. I can use a computer to do it. It'll do it for me. And I have a nice function that I can plot and work with. But what does it mean that f is built out of these two pieces? Can I say anything about the amplitude of f? Or the fact that f is an oscillating function? What's its period? What's its frequency? What is the relative importance of the two pieces I have written down here? So the real issue with Bessel functions is that for all of the mathematical power that they bring to approximation and to expansion in this way, and in their relationship with physical problems arising from the Bessel equation, once I have an expanded function, I can't just look at the terms and tell you anything about what f is doing. And so I'd really like, if I'm working with oscillating functions, to be able to pull that function apart in an expansion theorem that tells me all of the different components of the function in a way that could be interpreted. What I mean here is, I don't know how to understand what f is doing in terms of its pieces as a Bessel function. I don't know the frequency of those two pieces. I don't know how they're interacting with each other. It's great numerically, but in terms of understanding the behavior of f from a qualitative perspective, it's much more difficult. So the hope is that we can find another way to model oscillating functions that I can very easily read off all the different component pieces in a function, or that the basis for my vector space of functions is easier to understand. And so the hope is that in the same way that I've approached these last two types of series and these last two setups for expansion theorems, I could find another way to do it. And that's going to require a differential equation and an orthogonal family of functions and an expansion theorem. So what we're going to be moving into is trying to study periodic functions, not in terms of Bessel functions, but in terms of sines and cosines, because sines and cosines are about the easiest functions there are to understand. So this is what we want to do. We want to study oscillating or periodic functions, and we want to do it with an easy to understand basis of functions. And it would be really awesome if we could do it with sines and cosines. And this would basically be the ideal scenario. If I could do all of these things, then I could potentially just be given a periodic function f, pull it apart into sines and cosines and say, oh, look, there's a piece of this frequency and a piece of that frequency, a piece of that frequency, and these are their relative importance.